We've seen plenty of extreme weather events this year. Those would look like a walk in the park, apparently, if climate change led to a disruption of the Gulf Stream. Experts are keeping a close watch on that, and we are joined now by three of them. In Victoria, British Columbia, Brad DeYoung is a professor of physics and physical oceanography at Newfoundland and Labrador's Memorial University. In Vancouver, BC, Stephanie Waterman, professor of Earth and Atmospheric Sciences at UBC. And in Midtown, in Ontario's provincial capital, Kent Moore, professor of atmospheric physics at UTM, that's University of Toronto, Mississauga. And we're grateful to have the three of you on TVO tonight for a discussion I must confess I have not seen or heard much about, which is all the more important a reason why we should do it here tonight. And just to set this up, let me read this excerpt from the New York Times about the Gulf Stream system. The Times says it is one of the mightiest rivers you will never see, carrying some 30 times more water than all the world's freshwater rivers combined. In the North Atlantic, one arm of the Gulf Stream breaks towards Iceland, transporting vast amounts of warmth far northward, by one estimate supplying Scandinavia with heat equivalent to 78,000 times its current energy use. Without this current, a heat pump on a planetary scale, scientists believe that great swaths of the world might look quite different. Let's dive into this. Stephanie, how would you characterize the importance of the Gulf Stream for our climate and weather and our world as we know it?
Yeah, well, I think New York Times article does express how important it is. So the Gulf Stream is one of the ocean's main ways of transporting heat from lower latitudes up to higher latitudes. So we get a lot more energy from the sun near the equator and a lot less at the poles. And the role of this heat transport is to spread some of that heat out, and it lets the climate at more northerly latitudes be a lot warmer than they would otherwise be. Very important for climate dynamics.
Kent, what would you add to that in terms of our truly understanding the significance of this Gulf Stream?
Well, anyone who's visited, let's say, the UK and then has gone to Labrador, they're about the same latitude. So you'd expect them to have similar sorts of climates. The average temperature in northern Scotland is about 10 degrees Celsius, and the average temperature in Labrador is below zero. So you can just see the kind of huge impact that heat has. It makes wide swaths of northern Europe much more habitable than they would be if, in fact, the Gulf Stream wasn't transporting that heat northwards.
And just follow up, if you would, why does it seem to get short shrift? I talked to a number of people about this, and they didn't know about this.
Go ahead, Brad.
You know, we've only really known the Gulf Stream was there for about, a little more than 200 years. It was Benjamin Franklin who first mapped it out. He was the Postmaster General for the New England colonies, and he mapped out how quick ships would transit back and forth to the colonies from Britain, and found that there was this strong current there, and then showed how ships could use it going back and forth. But since having kind of discovered that, I think our general perception is that the Gulf Stream is a persistent feature of the ocean and unlikely to change. I think that's how all of us see the world around us, that, you know, it's there. Of course, it's going to be there tomorrow, and it's not going to change. But the other part of it is the Gulf Stream is tied to a kind of complex wind pattern that spins the water around the Atlantic basin. And I think even a lot of scientists felt that this wind pattern really wasn't likely to change very much, and that therefore, you know, it should be pretty reliable. It turns out it may not be as reliable as we had thought.
Well, Brad, I want you to, while you have the floor, pick up the story with something, again, that I had not heard of before, called the Atlantic meridional overturning circulation. AMOC. AMOC. What is that?
Okay. I feel like we should be on Sesame Street. We should have, Big Bird or something, and explaining how to pronounce meridional, which just really means north-south transport. And this whole AMOC discussion is tied to what Stephanie described, the role of the Gulf Stream, which is just one part of that circulation. And the Gulf Stream is carrying warm water to the poles. So if you think about it for a bit, if we're pushing a bunch of warm water to the pole, then either the poles are getting filled up with water or there's some return flow somewhere else. And what happens is there's cold water that sinks underneath the warm water and spreads southward towards the equator and then through the global oceans. And it's that movement of the warm water south at the surface and then the cold water underneath it that's the bigger picture, the AMOC. So the Gulf Stream's role is the surface heat transport. The rest of the transport is underneath in the deep ocean. And so this is the way in which this climate control system that we have, the warm water moving northward and the cold water moving southward, controls or adjusts our climate, and why it's so important if it got disrupted that the climate around for the rest of us who live in the atmosphere, for those of us who live in the atmosphere, would be messed up.
Now, Kent, I think we have a bit of a video presentation here that may further reflect what we just heard. So I'm going to ask our director, Sheldon Osmond, to roll that video, please. And Kent, as we watch it, maybe just describe what we're seeing.
Sure. So this is an animation from NASA. And so what you see here now is the warm water moving northwards up into that area where it's kind of dark. That's the Gulf Stream and the North Atlantic Drift. And then now as they zoom in, what you can see now are these arrows are descending. And that's when the warm water moves northwards, it's losing heat and moisture to the atmosphere. That water becomes dense and it sinks in a process that we call convection. It's exactly the same process that occurs in a pot of water. The only difference in the ocean is that the convection is upside down. So essentially the heavy water sinks to the bottom instead of warm air rising, which happens in the atmosphere. So that's what's happening. And so that loss of heat and moisture at high northern latitudes is really crucial, because if that doesn't happen, then as Brad said, the Gulf Stream can't transport heat any more water northwards. It has to kind of weaken or shift southwards.
Now, Stephanie, in terms of comprehending the vastness and sheer sort of size and power of this thing, well, let me put it this way. Astronomers often talk about how difficult it is for our brains to really comprehend, the vastness of the universe. Do we have that same problem as it relates to the vastness of the Gulf Stream?
I think so. I think the scales of the Gulf Stream, for example, and many of the features in the ocean are planetary scales, and they're much larger than the ones we're used to dealing with. The dimensions of the Gulf Stream, the width of this stream of water and its depth varies along its path, but it can be up to 100 kilometers wide, and it can extend through the whole ocean depth, so up to 4,000 meters tall. Someone once told me the transport of the Gulf Stream in terms of, in the context of an army, how many soldiers walking by per second. And so the transport, we measure the volume transport in millions of meters cubed per second, and it's equivalent to about 750,000 100-kilometer soldiers marching by every minute. So the scales of this transport, are much larger than the things we interact with, on a day-to-day basis.
Well, we got a hint of it in that first NASA animation, but then Sheldon, if you would, let's bring up that second shot as well. And this is a picture of the ocean circulation system. And again, it may give some indication what Stephanie was just talking about. This thing is, it's vast. And Stephanie, do you want to just take us through this graphic image briefly and suggest, well, it is massive. It goes everywhere. It's all over the world, isn't it?
Yeah, so this picture shows you the global scale of this overturning circulation. And some people call this depiction the conveyor belt depiction of this overturning. And so the red colors here that's the surface flow that we see on the upper limb of this overturning circulation. And we see, as Brad described, how the deep cold waters, which are in blue here, spread down from the North Atlantic, but that's then spread everywhere around the global ocean before rising up and becoming the upper level, or the orange part of this conveyor belt. And so this picture is a really good picture of how the scale of this current is global.
Gotcha. Okay, Brad,
and
let's go back.
That the time scale, if you think of the time scale for that circulation, it's upward towards 1,000 years. So it's a really large, really slow-moving current, but it could take 1,000 years for water to complete that cycle.
Take 1,000 years for water to make one cycle, the likes of which we just saw on that map.
Yeah.
Okay. Well, in which case, okay, can you take us back then to the previous ice age and what we learned about what happened to the Gulf Stream at that time?
Okay, so about 12,000 years ago, when the Earth was warming up in the last ice age, the Laurentide ice sheet, which covered most of Canada, was melting, and it was sending huge amounts of fresh water into the North Atlantic. And so there was a period of time which paleoclimatologists call the Younger Dryas event. Dryas is an alpine flower that usually grows in very cold regions, and they found pollen of this flower regions where it shouldn't be. And so that was the first evidence that there was this cooling. It lasted about 1,000 years. So for about 1,000 years, Europe suddenly went into a deep freeze. Temperatures in Europe probably dropped by about 10 degrees Celsius, probably in a lifetime. So this is something that would have happened sort of in someone's lifetime. And so Europe got really, really cold. And then eventually, over time, that fresh water was mixed away, and the Gulf Stream was able to resume. So what's important about the fresh water is that to get that sinking happening, as you saw in that video, you need to have the water really dense. And if the water is very, very fresh, that means that it's much harder for it to sink. And if it's harder for it to sink, then you can't transport as much heat northwards. So during the after the last ice age, when the Earth was warming up, Europe went into a deep freeze for about 1,000 years or so. And that's, if you like, the kind of most dramatic example of what we might see happening if the Gulf Stream weakens.
Well, that's where I was going to pick up the story. Brad, what's the significance of that revelation in terms of practical application today?
Well, the key issue is that, when you think back to those images where you saw heat being released in the Labrador Sea or in the Greenland Sea, warming the atmosphere there, that would stop happening. And so the weather patterns in the Northern Hemisphere would be enormously disrupted. For the moment, we're talking about how awful it would be if it was a total collapse. I don't think, even though that's in the discussion at the moment, that's the most likely thing to happen in the century we're in, but it's not utterly impossible either. And so basically the weather in the Northern Hemisphere would be nothing like we presently see. It would be a much colder, likely drier system. Storm patterns would change hugely. Ice conditions in the Northern Atlantic would all look very different. And so not just the Atlantic, because this influences the whole planet, but so the whole weather system of the Northern Hemisphere would be significantly disrupted. But for the moment, I don't think that's the most likely outcome. This idea partly has been in the scientific discussion as a serious consideration for several decades. And so there have actually been science programs going out to try to measure what's going on, because there was concern, partly from people experimenting with numerical models where they kind of dropped some fresh water at the surface and said, what's going to happen to this circulation? And what they discovered was even small amounts of fresh water could lead to significant changes. What Kent described in Younger Dryas, this event of a long time ago, was an enormous inflow of fresh water, we think, that caused this shutdown. But the models have showed that even a smallish amount of fresh water could have a really big influence.
Let us read the following excerpt. This is from a study this past August by Nicholas Boers from the Potsdam Institute for Climate Impact Research, who warns of, quote, early warning signs for a potential collapse. We're asking the question, could the Gulf Stream collapse, or a shutdown of the AMOC, which we talked about earlier? And here's what Nicholas Boers writes. He says, the signs of destabilization being visible already is something that I would not have expected and that I find scary. It's one of those events that should not happen, and we should try all that we can to reduce greenhouse gas emissions as quickly as possible. This is a system we don't want to mess with. All right, let's follow up from that. Stephanie, maybe start with this. When we talk about could the Gulf Stream collapse, physically speaking, actually speaking, when we use the word collapse, that would refer to what?
Well, as Brad said, there's different scenarios that could happen. Collapse, I think, suggests that the Gulf Stream is no longer transporting that water and that heat from the equator to the pole in the way it does today. I think there's a spectrum of things that could happen. That transport could slow down a lot, or it could cease. Collapse suggests cease, and so if that heat transport shut down, there would be knock-on effects in the ocean circulation and also the atmospheric circulation, that are complex and interconnected.
And Kent, how concerned do you think we should be about a potential slowdown or even shutdown of the Gulf Stream today?
Well, as Brad mentioned, we've been measuring the transport since about 2004. And over that period of time, we have measurements that show that the transport is decreased by about 10%. So that's a pretty significant decrease. Of course, with only a 16-year record and a cycle which has a timescale of hundreds or thousands of years, it's really hard to infer much from that. But I think it's one of these events we should be concerned about a potential slowdown, because that, again, would have knock-on effects, not as dramatic, of course, as if you collapsed it. But I think it's in the realm of possibility in the next century that we'll see this slowdown continuing. And, we'll see incremental cooling in, let's say, Northern Europe, even though the Earth is warming up. And again, changes to ocean circulation across the whole globe. So I think we should be worried about it. The collapse, I don't think will happen in anyone's lifetime, but I think we should be concerned about a slowdown.
And just to follow up on this, Kent, if the world is getting warmer, and we don't want that to happen because climate change is not a good thing for this world, and we'd like the temperature rises not to take place, but this has an influence of making the world cooler. Can you help me with this? Do these things cancel each other out?
Well, that's a good question. And I think people often think of the climate system as being a linear system. That is, the Earth warms up, the Earth cools down. But of course it doesn't. There's parts that that warm more rapidly. For instance, the Arctic is warming much more rapidly than the rest of the Earth. And so it's a nonlinear system. And so we could be in a situation, as we were in the Younger Dryas event, where a period the Earth was warming up after the last ice age, Europe went into a deep freeze. So it's possible to have these transient sort of events happen. Eventually, it'll work its way out, but it could be the case. And so the climate system is nonlinear, and there's a concern that we may be reaching what's called a tipping point, where there's sort of two states, and that's what Nicholas showed in his papers, that the Gulf Stream exists in either a very kind of rapid state, which we're in now, and then a very less rapid state. And so what Nicholas was talking about is this transition or tipping point where you suddenly transition from one state where the Gulf Stream is very active into another state where the Gulf Stream isn't as active.
Brad, any thought about what would happen to Canada under such circumstances?
Well, I mean, let me first go back to your earlier question about, is this a good idea? Because I'll just give you a kind of a counterexample to that in some sense. And that is, about 100 years ago, there was a proposal that a barrier, a dike, be placed across the Grand Banks of Newfoundland to stop the flow of this cold water that we showed moving southward. And the idea was this would warm the New England states, that the United States would have a much balmier climate and all would be good. And this was actually a serious suggestion made by one of the lead engineers for the Panama Canal. And it's under that category of, we now can control the Earth. And I think the idea that we get to control or to, control the temperature of the Earth the way you do your house with a thermostat is not a very good suggestion, because there are lots of unintended results of that. And so while this might appear to cool appropriately portions of the planet, it also utterly disrupts the whole kind of climate system, weather system within which we operate. And there would be very unhappy consequences for lots of people. So to your second question around how it would influence Canada, I mean, it would dramatically, obviously, most influence Atlantic Canada, since we're, bordering the Atlantic Ocean, and we're clearly seeing a major disruption of the the temperature and the conditions which we would see there, which would also disrupt fish stocks and shipping and all sorts of other things. But for Canada as a whole, it would shift the potential for agricultural activity across the country, change precipitation patterns hugely. And so it would not just be a little disruption. So what we've seen so far in the changes in weather, I would categorize relative to what we're talking about now as a small disruption. This would be a major disruption of weather. Weather would look nothing like it's looked in the last 100 years.
Stephanie, let me put this quote to you. And again, I may need some help with the pronunciation here. Scientist by the name of, it's either Wallace Broecker or Brecker?
Yeah,
I'm not
Broecker,
sure.
Yeah.
Okay. He developed the idea, apparently, of a global conveyor belt linking the circulation of the global ocean. And his quote is, "The climate system is an angry beast, and we are poking it with sticks." How do you like that as an analogy for what's going on right now?
Yeah, I don't know. I wouldn't say angry. A complicated, complex, vast, interconnected in ways that some ways we understand and other ways we don't understand. Poking it with a stick, I think, is maybe appropriate in that I don't think we have a full understanding of how perturbations to one part of the climate system will impact all these other interconnected systems in the ocean and in the atmosphere, in the biosphere. And so, so I think that the poking with a stick is sort of a reference to we are altering the system and suggesting alterations perhaps through geoengineering. But we don't, they're very crude, these tools, and we don't, and the beast part, we don't understand the complexity of the response of that. Angry is a bit emotive, but complex, yes.
A little too much anthropomorphizing there maybe on his part, but put it this way, the suggestion certainly seems to be that we are poking with a giant stick, and we're doing so not having a good enough understanding of the outcomes that we may be responsible for. I mean, is that a fair observation, Stephanie?
Yeah, I would agree with that wholeheartedly. We appreciate the complexity, but we don't understand all the interconnections and the complexity. So understanding the knock-on effects of actions, I think most climate scientists would feel that we don't have a good understanding of all those knock-on effects.
Okay. Kent, let me try this. Everybody seems to think of climate change as a very gradual thing that will take place, 2 degrees over a several decade period of time. But then you referred to a tipping point earlier. And I wonder whether this effect that we're talking about, all of a sudden, it's like the house of cards falling down. You can do a little bit and nothing much happens, and then boom. Is that potential here?
I think that's the concern. I think it's safe to characterize global warming as mostly linear. I mean, we're just warming the planet up. But then we can have these knock-on effects where suddenly there's a big transition. And the one I like to think of is just freezing. Like in Toronto in the winter, our temperature's around 0, right? When it's -2, everything is frozen. When it's +2, everything gets slushy and you get splashed by cars, as you walk down the street. And so there's an example of a tipping point where water melts at 0 degrees. And so if you go through that point, you suddenly have a very different climate system. And that's, I think, a sort of metaphor maybe for what a tipping point is, one of these sudden changes that happens because the system is highly nonlinear. That means that the responses may not be the same as the inputs. And I think that's really the concern. The Gulf Stream is probably the poster child, if you like, for these tipping points. But there's other ones. Losing Arctic sea ice is another one who have a dramatic transition. Losing land glaciers. There again, these are really dramatic changes. So the Gulf Stream is probably the most dramatic of these. But the climate system is full of these nonlinearities that could, if you like, bite us if we poke too hard.
Brad, if the Gulf Stream system were to weaken, or God forbid, even shut down, is there anything at that point that could be done about it?
Well, that takes us into this kind of category of trying to, instead of poking at the bear or the angry animal, to throw a net over it or something to try to contain it. And, if you go back to our description of how enormous the Gulf Stream is, That's a pretty big animal to throw a net over. And so the suggestions for geoengineering the responses to these problems have so far not looked more appealing than the problems themselves. And so I think the short response is no, not likely. And it's really why I think in this broader discussion about climate change and putting CO2 into the atmosphere, there's a lot of focus on trying to stop us reaching a particular temperature change, 1.5, whatever, 2 degrees. We don't want to get to that point. But what this discussion shows is there isn't an absolute point where we need to worry about things like this. These things could happen, this kind of tipping point, somewhere along the line of from where we are now to those 1.5 or 2 degree temperature changes. So anything we do that slows down or stops us from reaching those points is a good thing, even if we only get to 1.4 or 1.6, because just thinking of Kent's analogy, if the tipping point is at 1.9, then we for sure don't want to reach that point. The problem is we don't know where these tipping points are in the system. We know they're there. We know that we're close to them because the whole system is basically, hasn't really changed substantially. And so the tipping points aren't far away, that we're certain of. And so the question we don't know the answer to is, how far away are they? And at what point when we poke at this bear or whatever animal, is it a bear? Something else. At what point does it get really upset and tip over? And the less we poke, the less CO2 we put into the atmosphere, the better.
And Stephanie, just finally, is there a preferred geoengineering solution here that scientists are somewhat in agreement on?
Yeah, well, I liked when Brad said that those solutions don't look more attractive than the problems we're facing right now. I think there are some ideas out there, but I don't think that any of them have been deemed feasible or have been tested. And again, the knockoff effects of perturbing the system, I think, cause scientists a lot of concern. And so I wouldn't say that there's a geoengineering solution out there that I feel confident in at all.
Kent, how about you? Last word to you on this issue. I guess we've all agreed it's a bear. We've all agreed we shouldn't poke the bear. But is there a geoengineering solution out there, notwithstanding?
I don't think so. And as Stephanie mentioned, that every one of them has some problem. The scale is enormous. I mean, just think of how much energy is in the Gulf Stream, right? It's just enormous. The other concern I have is that it diverts us from the real pressing issue, which is getting our carbon emissions under control, right? If there's this magic bullet that we can suddenly put a big sail up in space and reflect sunlight, back out in space, it detracts us from the real problem, which is we need to get our carbon emissions under control. And that's really the only way that we can contain the warming and make sure that we don't reach these tipping points. So no, I'm not in favor of any of these geoengineering solutions. They're all have unanticipated consequences. There's a huge record of us trying to do things and screwing it up, right? I mean, that's what we do as humans, and I think this is another example of a way that we would probably mess things up even worse than what we were trying to solve for. So no, I don't think it's a feasible solution.
So note to self, don't poke the bear. We got it. I want to thank the three of you for joining us from near and far tonight for a really fascinating discussion. Stephanie Waterman in Vancouver, British Columbia, Brad DeYoung in Victoria, BC, Kent Moore from UTM in Midtown Toronto. Stephanie, I'm sure it's been observed by many in the past, you do have the perfect last name for the kind of work that you ended up in, right?
It's true.
I mean, come on. For an Earth, Ocean, and Atmospheric Sciences person to have a last name Waterman, I mean, come on, give me a break. Well, there we go. Thanks, you three. Be well.
Thank you.
Okay.
Thank you,
Steve.
The Agenda with Steve Paikin is made possible through generous philanthropic contributions from viewers like you. Thank you for supporting TVO's journalism.